Good morning, students. Chapter 7, System of Particles and Rotational Motion. Yes, today we will see one important topic, that is conservation of angular momentum. What is conservation of angular momentum? That you already know, but what is its use, application, that we will see to it. Okay, see here. Conservation of angular momentum. We know that torque acting on body tau is equal to dl upon dt. So if resultant torque tau is equal to 0, so therefore dl upon dt is also 0, and therefore angular momentum is constant. Angular momentum is constant. Yes or no? Yes. Angular momentum constant means I can write it is I omega also constant. Angular momentum L, that is nothing but I omega, where I is moment of inertia and omega is angular velocity. So I omega is also constant. So if you are given any situation, okay, one body is rotating. So if that body is rotating such that there is change in its moment of inertia, yes, I omega remains constant. It means if there is change in moment of inertia, there is also change in angular speed, such that their product remains same. When torque acting on it is 0. Okay, so yes, I omega is equal to constant. We have to use this condition to solve some questions and to understand some phenomena. For example, see, I omega is equal to constant. Clear? That is angular momentum is constant. Okay, if you are sitting in a chair that is rotating, okay, on wheels, okay, and yes, if you are sitting in a chair and your friend tries to rotate you, okay, by applying some force. Yes or no? Yes, then you are rotating. Okay, feel or experience the speed by stretching your arms outside and fold inside. You will experience some change in speed. Yes, you will experience some change. Okay, when your hands are folded like this, okay, and if you stretch your arms outside, yes, if you stretch your arms outside, there is change in speed of rotation. Okay, some dancers, while they are dancing, okay, they try to fold their hand like this, okay, and then they rotate. So whenever they are rotating by folding their hands, okay, or by keeping their hands close to their body, their speed increases. And when they stretch their hands, their speed decreases. So what is reason behind it? We will see by taking one example. Okay, see here. Suppose the earth suddenly contracts and its radius becomes r by 2, where r is present radius of earth, keeping its mass same, then what will be length of the day? You have to find what is length of the day if radius of earth suddenly contracts. Now see, earth, we can consider earth as solid sphere. Okay? Yes. Okay. So earth as solid sphere. So now for solid sphere, moment of inertia. Its equation is I is equal to 2 by 5 mr², where m is mass. Where m is mass and r is radius. So see here, suppose the earth suddenly contracts and its radius becomes r by 2. So see, if radius becomes r by 2, then obviously moment of inertia changes. Yes, then there is also change in its speed, and if speed changes, there is effect on time. There is effect on time. Yes, there is effect on time. So see here, how to calculate this whole sum? How to calculate this whole sum? See, here it is. Here it is. Yes, suppose the earth suddenly contracts by itself. Okay, so yes, resultant torque is 0. Then according to law of conservation of angular momentum, law of conservation of angular momentum. How to write? Yes, initial momentum is equal to final momentum. Initial angular momentum is equal to final angular momentum. It is before and it is after, and it is after. Clear about this? Okay, L is equal to constant. It means we can write initial angular momentum is equal to final angular momentum. Now what is equation of angular momentum? See, I1 omega 1 is equal to I2 omega 2. Moment of inertia before contraction, after. Angular speed before, angular speed after. Now I, for solid sphere, what is equation of moment of inertia? I is equal to 2 by 5 mr square. Okay, to see how to write this. Here I1 means is 2 by 5 m r square, because at present its speed is r. At present its speed is r, so it is mr square omega 1 is equal to, okay, 2 by 5 m. Suppose the earth suddenly contracts and its radius becomes r by 2. So now I have to write it is as r by 2 whole square omega. Clear? Okay, so yes, it is easy. So see, this 2 by 5 and m. Now how to simplify this? So yes, it is r square omega 1 is equal to, it is r square by 4 omega 2. R square by 4 omega 2. R square cut. So therefore, omega 2 is equal to 4 omega 1. Omega 2 is equal to, it is 4 omega 1. It means if radius of earth becomes r by 2, speed of rotation of earth becomes 4 times. Speed of earth of rotation becomes 4 times. So what is effect on time? What is effect on time? Yes, we know one equation. That equation is omega is equal to, it is 2 pi upon t. Omega is equal to, it is 2 pi upon t. So see, here it is. Omega means is 2 pi upon t2 is equal to 4. Omega 1 means is 2 pi upon t1. 2 pi cut, 2 pi cut. So t2 is equal to, it is t1 by 4. T2 is T1 by 4. Okay, so what is meaning of this? See, understand carefully. Radius of earth becomes r by 2, means decreases. Here, radius decreases. Okay, then as radius decreases, according to this equation, that is I is equal to 2 by 5 mr square, moment of inertia decreases. Moment of inertia decreases. Okay, and according to law of conservation of angular momentum, see, omega 2 is equal to 4 omega 1, means angular speed increases. Angular speed increases. Angular speed increases. Angular speed increases. So now you can understand that example. Okay, if you are sitting in chair and it is rotating whenever you stretch your hands outside, the distance increases. Distance increases. Moment of inertia increases and speed decreases. Opposite to this. Okay, and whenever you bring your hands close to your body, hands close to your body means that distribution of mass comes nearer to your body. Distribution of mass comes nearer to your body. So radius decreases, moment of inertia decreases, angular speed increases. And yes, if angular speed, hello students, you know that if speed increases, it takes smaller time. So yes, angular speed increases, then time decreases. Clear about this? So yes, it is one example from which you can easily understand the concept of conservation of angular momentum. Clear about this? Yes, radius decreases, moment of inertia increases, angular speed increases, and time decreases. You can also remember it's another way. Okay, if radius increases, then moment of inertia increases, then angular speed decreases, and then time increases. Clear about this? So yes, you have to remember this one. Last, also here, this question I can ask with different changes. Radius becomes r by 2. I can replace radius becomes r by 3. Yes. I can replace radius becomes r by 4, r by 5, r by 6. Then how to find speed and time? You can find directly. So for such cases, okay, for Earth or for sphere, or for Earth. See here, if radius becomes r by 2, means I am writing general equation. Okay, so if radius becomes r by n, yes, 2 is replaced by n. If radius becomes r by n, then what about angular speed? It is 4 omega 1, means 4 times. Angular speed becomes 4 times. Angular speed, it becomes 4 times. 4 means 2 square. So is equal to it is 2 square. Or you can say it is n square. N square omega. Here, yes, here n is equal to it is 2. So put n is equal to 2. 2 square will be 4. Yes or no? Yes, it is. Okay, what about time? So see, time is equal to it is t1 by 4. So yes, you can write it as t upon n square. It is t upon n square. So if radius becomes r upon n, angular speed becomes n square omega, and time becomes t upon n square. Yes, also here, if radius becomes n times, then angular speed becomes omega upon n square, and time becomes n square t, Clear? So yes, such changes you have to remember. Clear about this? Okay. So yes, you have to remember these all things. About conservation of angular momentum. And yes, this concept is important. It is one question to understand what is conservation of angular momentum. Okay, now you can easily understand why some scatters and some dancers, okay, they fold their hand when they are rotating. Clear? Okay, we will see one another question. See. Now we will see one example. See, a question. A thin ring of mass capital M and radius capital R is rotating about axis passing through its center and perpendicular to its plane with angular velocity omega. 2 point objects having mass small m are attached gently to the opposite ends of its any diameter. Then angular velocity of ring will be. See, first of all, whenever you are given such situation, you have to draw figure. Okay, what is initial condition and what is final condition? See here. Initial condition. A thin ring of mass capital M and radius capital R. Yes. It is ring, a thin ring of mass capital M and radius capital R is rotating about its axis, passing through its center and perpendicular to its plane with angular velocity omega. So omega 1 is equal to, here it is omega. Simple. Yes. Now, 2 point objects M are attached gently to the opposite ends of its any diameter. So what is final condition? So what is final condition? See, what is final condition? Ring, it is same, axis is same. Okay, initially it was ring only. Now 2 point objects M are attached gently to the opposite ends of its any diameter. So for example, I am taking this diameter, 1 point here, another point here, its mass is M, its mass is also M. Okay, so your question is, okay, now what is angular velocity of ring? What is angular velocity of ring? Do you understand question? Okay, in initial case only ring is rotating. In this case, ring and 2 point masses they are rotating. Then how to find this? Yes, according to law of conservation of angular momentum. Okay, according to law of conservation of angular momentum. Initial momentum is equal to final momentum. Initial angular momentum is equal to final angular momentum. So I1 omega 1 is equal to I2 omega r. Okay, now see here. Okay. Initially, only ring is rotating about an axis passing from its center and perpendicular to its plane. And yes, we have obtained its equation. That its equation is moment of inertia of ring about its axis passing from center perpendicular to its plane is mr square omega 1. Any doubt? Okay, yes, you have to remember this equation. Yes, you can also remember this equation from table. Yes, from table is equal to I2. Now see, in final case, not only ring is rotating, but 2 point masses are also rotating. So here, what is total moment of inertia? Total moment of inertia means moment of inertia of ring plus moment of inertia of these two particles about this axis. Again, in initial condition only ring is rotating. So yes, it is its moment of inertia about this axis. But in final case, ring and these 2 point masses are rotating. So what is total moment of inertia? Mr square, that is moment of inertia of ring. Now for this particle. Okay, see, its mass is m and its distance from x-axis is nothing but radius. So yes, it is m r square. Plus, it is also particle. Distance from this axis is m. So yes, it is plus m r square and omega 2. As they are rotating together, so their angular speed will be same. To understand what is difference between these two conditions. Okay, here only ring is rotating, here ring with 2-point masses are rotating. So how to write equations? Clear about this? Now it is simple. See, it is m r square omega 1 is equal to, here it is m r square plus 2 mr square omega. So yes, it is m r square omega 1 is equal to r square common. So I can write it is m plus 2m omega 2. R square cut. So therefore, we have to find final angular velocity. Okay. So omega 2 is equal to, it is m upon m plus 2m omega 1. And yes, it is your answer. Clear? So yes, it is question ke how to find angular speed. You have to first of all draw figures. Okay, if you can understand this data, what is initial condition, what is final condition, then you can easily say, okay, yes, how to write the equation of moment of inertia, about which axis. You know that table for moment of inertia. Okay, so it is one question which is based on conservation of angular momentum. Clear? For today, this is it. In next lecture, we will see what is difference between translational motion, rotational motion, and the most important topic, rolling motion. In next lecture. For today, this is it.